Analyzing graphs of functions. The graph of a function. In our last video of section 1.4 of our Larson text, Precalculus 11th edition, we talked about the fact that a function can be represented verbally, numerically, as an equation, or graphically. So in this section, we're going to focus on the graph of the function. Before we talk about any aspects of the graph, let's determine if this graph does in fact represent a function. So if you'll recall, we learned something called the vertical line test. And the vertical line test said if we can draw a vertical line anywhere along the graph and only ever hit just one point on that graph, then the graph does represent a function. And as you can see, I've drawn 5 different vertical lines, and all of them hit the graph at only one point, and there's no point at which I could draw a line that is vertical and hit 2 points. Therefore, this is considered a function. Now let's continue reviewing what we learned in our last video. Let's determine first the domain of the function. Remember that the domain of the function is going to be the x values that our function can take on. Now in our last video, typically I would give you an equation like y equals x squared minus 4, and it was up to us to determine that the domain, because this is a polynomial equation, would be all real numbers. This is a little different because, as you can see, I'm dealing with a specific graph that is contained within certain values. So the domain is going to be those certain x values. So my first value occurs at the x value of -2, and my last value occurs at the x value of 3. Now, the question then becomes, how do we represent that? So we're going to do a quick review, hopefully review, of interval notation. Interval notation is if a value is included in the domain or in the interval, we're going to use a closed bracket. So a closed bracket represents that the values are included in the interval, whereas an open bracket would represent that the values are not included. So what does that mean? Well, let's take a look at our graph. At -2, 11, we can see I have a closed circle. A closed circle indicates that -2 is in fact included in the domain. Now let's look at 3. At 3, 4, I have an open circle. An open circle represents that that value is not included in the domain. So we're actually going to have a domain that is not closed or open, but is closed on one end and open on the other. So that's going to look like -2 with a closed bracket, 3 with an open bracket. This indicates -2 is included, 3 is not. Let's do the same for our y values, which is our range. So now we're looking at y, so I'm going to get rid of all of my markings and instead focus on y. So the greatest value appears to be +4 and the least value appears to be -11. In the same way that we did on the last one, we know that this is a closed circle and this is an open circle. And so my solution for range will be that the least value is -11 and it's included, and the greatest value is +4 and it's not included. Now let's take a look at the values of the function. The values of the function tell us to use the x value that is given. Remember, it's f of x. And our output is going to be the y value at that point. So for -2, I'm going to go to -2 and see that the point is at -11. So my solution for f of -2 is -11. My solution for f of 0 is at 0, 1. So my solution for f of 0 is 1. And again, that just means there's a point at 0, 1, and there's a point at -2, -11. For f of 3, I know that I have an open circle. So I cannot say that f of 3 is equal to 4 because it is not. There is not an actual point at 3, 4. Our graph approaches 3, 4, but it stops just short of there. So f of 3 is undefined. Zeros of a function. Also in our last video, we did talk about the zeros of a function, but I am going to teach it as though you don't know what a zero is. So let's recall that a zero of a function is where our function is equal to 0. So that means I'm just going to set each of these equal to 0 to find the zeros. Graphically, it's where the function is going to cross the x-axis. Now, there's different strategies for finding the zeros, and a lot of that is based on the type of function that you're dealing with. So, for instance, this is considered a polynomial function. Poly means many, nomial means number. So a polynomial function has a degree of 2 or greater, and it doesn't have anything like the square root or a function divided by another function. It's a polynomial. The domain is all real numbers. The second function is considered a radical function because, whoops, I forgot the C, a radical function because of course we have a radical. So that doesn't matter if it's a square root, a cubed root, a fourth root, and so forth. Those are all radical functions. The last is considered a rational function. Ratio, of course, is where rational comes from, and ratio or rational means that we have a ratio of two separate functions. So if you'll notice, it's not just any fraction, it's a fraction that contains a function divided by another function. So if you're dealing with a polynomial function, most often we're going to talk about how to factor. Now, this is not a video on factoring. So if you are not comfortable with factoring, I will link all of the factoring videos in the video description, and you can go back and look at different ways to factor. So when I factor this particular question, I'm going to use something called amazing factoring. And that starts with finding A times C, comparing it to B, and then writing the two binomials. So you might be saying, okay, great, what's A, B, and C? Well, in a quadratic is where we have a polynomial of degree 2, we are going to look at A being the value multiplied by x squared, B being the value multiplied by x, and C is the value that is a constant. Notice when I've boxed those, I've included the negatives on those values that are negative. So in this case, A times C would be 2 times -3, which is -6. Now, we're going to compare this to B. We're going to look at numbers that multiply to -6. So that could be like 1 and 6, and I'm not going to include signs quite yet. 1 and 6, or 2 and 3. So both of those multiply to 6, but I need B. I need the addition of the 2 to add to -1. So I know the difference between 1 and 6 is 5 because 1 minus 6 would be -5, 6 minus 1 would be +5. If I add 2 and 3 or find the difference between 2 and 3, 2 minus 3 would be -1, and that's what I want, which means I need a +2 and a -3. Now, do +2 and -3 multiply to 6? Yes. And when I add them, do I get -1? Yes. So now we're going to factor. And to factor, we're going to say 0 is equal to, and then we're just going to say x, and this is where the a part comes in. So remember that a was 2. I'm going to use +2, but I'm going to put 2 over a. And then I'm going to say x, and I'm going to say -3, but I'm going to put 3 over a. So this looks maybe a little bit different than what you're used to, but I get x plus 1 and I get x minus 3/2. But I don't really like that, so what I'm going to do is I'm going to move the denominator to the front. So I get 2x minus 3. This is the correct factorization. What are the zeros? The zeros are if I set each of those binomials, each of those two terms, I set them equal to 0. So again, I'm not going to show the work there. X plus 1 equals 0. I would subtract 1 from each side. I would get -1. And then 2x minus 3 equals 0. I would get positive 3/2. So if you'll notice, it's these values here with a change of sign. So it's +1 and then -3/2. I've just changed those signs. Now, check it graphically. If you can see, this is the graph of that function, -1, 0, and 3/2 or 1.5, 0. Now let's take a look at the radical function. So for a radical function, again, we're just setting it equal to 0. To start solving this, I'm going to square each side. So that gives me 12 minus 2x squared is equal to 0 squared, which is 0. I'm going to subtract 12 from each side. I'm going to divide each side by -2. And then I'm going to take the square root of each side. So I get plus or minus radical 6. And those are the zeros. Now, plus or minus radical 6, we don't have an exact number for because that's an irrational number. But it's about -2.44, I can't read the writing, 85, I believe. Anyway, it's radical 6. So that is what the graph of that function looks like. If you'll notice, we've talked before about the domain of a function. And if you'll remember, the domain of a radical function is that the radicand has to be greater than or equal to 0. So if you'll notice, there are no negative values in our graph. For our last example, we have a rational function. And when we talked about the domain of a rational function, we said that the denominator cannot equal 0. So t can't be -3. So that will be fun to keep in mind as we look at the graph. To find the zeros, we're going to set the numerator equal to 0. So 4t minus 7 is equal to 0. 4t is equal to, by adding 7 to each side, t is equal to 7/4 or 1.75. So let's take a look at the graph of that function. We can see this is the 1.75, 0, but at the point of t equals -3, there's actually an asymptote. And that is a line that the function approaches but never touches. Here are 3 similar questions for you to try on your own. For the first, I would like you to use the quadratic function. Remember that the quadratic function is x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Again, this is a, this is b, and this is c. Again, I would like you to find the zeros for each of the functions and then check them graphically. So press pause, try all 3 questions, and then press play to see how you did. So beginning with the first one, and I'm not going to go through each in such great detail as I did on the last one, just for the sake of time. I did use the quadratic formula to find that the zeros are 1.5 and -8, and by checking that graphically, I can see that is where the parabola crosses the x-axis. For b, which is a radical function, remember we're just going to set it equal to 0. We're going to square each side, and I end up with t is equal to 25. If I check that graphically, I can see 25, 0 is in fact a point on my graph. And for the last, which is a rational function, again, I'm only worried about the numerator. So I'm setting the numerator equal to 0 and finding plus or minus radical 2, which is about 1.41421. And we can see the graphs do match up with what we found algebraically. Increasing and decreasing functions. Another property of graphs that we need to be aware of is whether the function is increasing or decreasing. So a function is increasing on an interval when for every x1 and x2 in the interval, if x1 is less than x2, or as x increases, that implies that f of x1 is less than f of x2, or f of x increases. So again, we're just looking at a graph that is increasing from left to right. And we're looking for a specific interval. So I've drawn an equation that's obviously linear that will be increasing over the entire interval, but you might get a crazy graph that increases, stays constant, and decreases. So a function is decreasing on an interval when for any x1 and x2 in the interval, x1 is less than x2 implies f of x1 is greater than f of x2, or as x increases, f of x decreases. So simple example. And obviously constant on an interval when as x increases, f of x stays the same. So you're just going to have like a constant function, pretend that's a nice straight line that is neither increasing or decreasing. So let's look at a few examples to determine where a function is increasing or decreasing. For the first example, I can see that the function is increasing up to this point. So for increasing, I'm going to say from negative infinity to the x value of -1. And then it is decreasing from -1 down to +1. So again, I'm only concerned about the x value. So from -1 to +1. But then I can see that the function increases again from 1 on to infinity. So I'm just going to put a union sign, and then from 1 to infinity. For my next graph, it appears to be increasing from negative infinity up to 0. Again, we only care about the x value where that changes. From 0 over to 3, it appears to be constant. So from constant is from 0 to 3. And notice these are all open intervals. We never would close an interval when we're talking about increasing, decreasing. And then it would decrease starting at 3 and going on to infinity. And for my last one, if I can see it's increasing, it's increasing, it's increasing the entire time. So it's always increasing, so that's negative infinity to positive infinity. Relative minimum and relative maximum values. Another graph property is the relative minimum or relative maximum values. And again, in white, I have included the official mathematical explanation, and in yellow, I have included what it means to you and I. So a function has a relative minimum of f of a when there exists an interval x1, x2 that contains a such that x1 is less than a is less than x2 implies f of a is less than f of x. What all of that means is over an interval, and it doesn't matter which interval, the value of f of a, so the y value, is less than all of the other f of x values. So let's take a look at our picture that we used in our last video example. And I can see that while there are certainly values here that are less than -2, if I were to look, say, just at this interval, that the point -1, -2 is the lowest point in that interval, which means there is a relative minimum of -2. So the minimum is the y value only. The location is the point. 1, -2. In the same way, a relative maximum occurs when if x sub 1 is less than a is less than x2 implies f of a is greater than or equal to f of x for all of the other f of x's surrounding it. So again, if I look at an interval, and I'm going to close this interval off just a little bit more. Let's close it off right here. Within that part that I have closed off, I can see that while even though these values continue to be greater than positive 2, those values aren't in my interval. I can contain an interval to wherever I want. So this isn't an absolute maximum, it is a relative. And that means relative to everything around it, is it greater than everything around it? So a relative maximum in this case would be a maximum of 2 at -1, 2, because again, this is greater than all of the values around it. You can also use your TI-84 to help you locate a minimum or maximum. So to find any relative minimums or maximums for our specific equation, f of x is equal to x cubed minus 3x, we're first going to go to y equals, type in x to the third power, arrow over, minus 3x, and then we're going to click graph to inspect the graph. Now we can see that this is the same graph that we've been looking for. One option you can use is to trace. I don't like this option because it very rarely gives you the actual maximum. So what I would encourage you to do is choose second and trace, which is the calc function. And so I can choose minimum or maximum. So let's do the maximum in this case. Now the maximum, notice it says left bound. I just need to arrow over to the left of the point that I'm looking for. So I'm going to choose, and it doesn't matter. So I can choose right here and press enter. On the right side, it will matter because I am going to have to choose a point before the function increases beyond what I'm looking for. So I'm looking for the coordinates of this particular point right here. So I'm just going to choose something to the right, and then you click enter, and then it gives you the maximum value. X is -1, so that's the location, -1, 2, and the maximum is 2. You could do the same thing for the minimum. Average rate of change. Continuing our study of the graphs of functions, let's talk about the average rate of change. We know that we can find a rate of change of a linear function by simply using the slope formula, which is y2 minus y1 divided by x2 minus x1, and we call that the slope. Well, essentially, for a nonlinear function that we have here, we can find something called the average rate of change, which is simply the average slope over a certain interval. And so the interval will be defined by whatever coordinates of the graph that we are given. So for instance, this is the equation of the graph. Y is equal to x cubed minus 3x that we've been working with throughout this video. And I want to find the average rate of change of f, which is the function graphed in blue, from -2, -2 to -1, 2. So I'm looking for the rate of change of this dotted line, which means I'm really just finding the slope of that line. So I'm going to say m secant, because this is called a secant line when we're connecting 2 points of a nonlinear function. And I'm simply going to find the slope. So 2 minus -2, so that's the second y minus the first y, divided by the second x, -1, minus the first x of -2. So simplifying, I would get 4 divided by 1, which is 4. So the slope of this line is equal to 4. If you would, press pause and try the second part of that question on your own to find the slope of the secant line from -1, 2 to 1, -2. Press play when you're ready. Hopefully you found the slope of the secant line to be -2, and that makes perfect sense because obviously we're pointing down as we go from left to right. Let's take a look at an application involving the average rate of change. If the distance in feet of a moving car is from a traffic signal is given by the function s of t is equal to 25t to the 3/2, where t is the time in seconds, we're to find the average speed of a car from the time t equals 1 to the time t equals 4. So never a bad idea to take a look at the graph of the function so that we understand exactly what we're going to do. Now we know in order to use the equation to find slope, we need two ordered pairs, and we don't have two ordered pairs. What we do have is two x values, t equals 1 and t equals 4, and we can use the function to determine the y values. So f of 1 is simply plugging 1 into the function to get 25, and f of 4 is plugging 4 into the function to get 200. So now we have two ordered pairs, 1, 25 and 4, 200, and now we can find the rate of change simply by using that slope formula. So our rate of change, average rate of change, is 58.33 feet per second. Even and odd functions. We're going to finish up by taking a look at even and odd functions. An even function is a function that's symmetric to the y-axis. So again, that is the y-axis or the vertical axis. These are functions that can be folded in half across the axis. So that's what we're looking at for even functions. And even functions are functions where f of negative x is equal to f of x. So to check for this, obviously we can graph this and see very clearly that the first equation, y equals 2x squared plus 3, is an even function. We can see that because if I took this part of the graph and folded it over to the other side, it would match perfectly with the other side of the graph. Whereas for my non-example, if I took this part of the graph and folded it over, it would not match up perfectly, so it's not an even function. But let's talk about how to do this the mathy way. To do this, we're going to find, remember that y equals is the same as f of x. So we're going to think of it as f of x, and we're going to find f of negative x. So f of negative x would be 2 and then negative x squared plus 3, and then we would simplify. Negative x squared would be negative x times negative x, which is positive x, which gives me 2x squared plus 3. So f of x is 2x squared plus 3, and f of negative x is 2x squared plus 3, indicating it is an even function. For a non-even function, that's not going to be the case. So f of x is equal to x cubed minus 3x. F of negative x, again, I'm going to replace the x with a negative x, and then I'm going to simplify. So negative x to the third would be a negative times a negative times a negative, which means it's negative x cubed. And then minus 3 times minus x is plus 3x. And I can see that this function does not equal this function, so this is not an even function. Odd functions are symmetric to the origin, so we can think of them as having rotational symmetry of 180 degrees, or symmetric to the line y equals x. So the line y equals x is this line, and I can see by looking at that line that my odd function is in fact symmetric to the line y equals x, and the non-odd function is not symmetric to that line. And by symmetric, I mean that I could fold it across that line and get the same thing. Now, to me, that's sometimes difficult to visualize, and so I think of it as the rotational symmetry. I think about this is the second quadrant, and could I rotate that around, and would that be in the fourth quadrant? And yes, it would. I see that I've got a hump, and here I have a hump. And if whatever's in the first quadrant, could I rotate that around, and would that be in the third quadrant? And again, in the first quadrant, we have this line, and in the third quadrant, we have this line. And I can see that that does appear to be rotated around. Mathematically, we're going to find f of negative x and we're going to find negative f of x. So f of negative x, just as we did before, negative x to the third minus 3 times negative x, and we're going to simplify to negative x cubed plus 3x. Then we're going to find negative f of x. So negative f of x means take everything in here times negative 1. So that would be negative x cubed, and then negative 1 times negative 3x would be positive 3x. And I can see that these are the same, and therefore this is an odd function. I'll do the same here. F of negative x, 2 times negative x squared plus 3 would turn into 2x squared plus 3. Whereas negative f of x would be negating both terms, so that's negative 2x squared minus 3, and these two are not equal, so that is not an odd function. Up next is section 1.6 in your text. It is a library of parent functions.